this video, we first start by going to our model wizard where we select our space dimension. So we'll be dealing with 2D axisymmetric space dimension. Then we'll select our physics. So we go to our acoustics where we'll select, we go to thermoviscous acoustics where we'll select this first one. So we add this, then we'll also add electrostatics to our work. Okay. So after adding these two physics, we go on to structural mechanics where we add the membrane. Okay. So our membrane and the dependent variables shown in here, as you can see. We want to make some modifications to the dependent variables for the thermoviscous acoustics. Pressure is P, U, V, W, T. Temperature variation is T. Okay. Now the membrane, make here UM. We want to name this UM. We want to name this side to UM. To name this VM. We want to name WM. Move to our steady. And over here, we'll not add any steady for now. So we click on done. No. Okay, so that brings us to our work. So with the parameters, we'll manually input our parameters that we're working with. So I'll input them one by one. It should take a little bit of time. I'll be done shortly. So as you can see, we have the HM. 2 microns. TM 7. I have G is 3 times 1. I have TM, which will be the 150. Since we have this is 800 kilograms. We have pin, which will be pressure. The external incidence pressure, then the pressure release, to be 0. We have membrane elastic modulus, so 1 PN. We have the membrane's Poisson, which will be 0.4. We have the polarization voltage is 0 volts. We have pre-amplifier, which will be 1 ohms. Okay, so let me check. We have this membrane radius, we have the air gap thickness, membrane thickness, and let me name all. This is the membrane radius. This is the air gap thickness. This is our slit gap width. This will be our membrane static tension. This will be our membrane density. So these are slits. So we have our membrane radius, air gap. This is rather the membrane thickness, and this is rather the slit gap, which is the membrane static tension. And this is the membrane density. This 1 PA is the external incidence pressure. This is the pressure. Release pressure. This will be our membrane elastic pressure. Modulus pressure. This membrane Poisson ratio. And we have our polarization voltage. We have our preamplifier. Amplifier output response. We have our, we should include membrane surface density, which will be times Q. Membrane surface density. Okay. Okay, so after inputting our parameters, can go ahead and start building our geometry. We'll start building our geometry. We'll first add a rectangle. Add a rectangle, and the width and the height of the rectangle will be we'll add the rectangle, and the width of the rectangle will be R N E M, and height is H. Go ahead to build selected. It builds it simply. We'll add another rectangle, where the width will be G, height will be H M. This to be H M. We want the R to be at R N E N. Membrane G minus G. Okay. So as you can see, we have it over here. 4 million, and we built all. So we have formed our two rectangles. And go to definitions, and we want to add explicit, where the boundary will be at 3 and 6. So this label will be the membrane as you can see. Look at the view axis, the view scale. Let's make it automatic. Let's update it. As you can see, we have modified the view scale. Yeah, we go ahead to add material, where we'll add, first add air, adding air to our material, to our work. in there, you can see the properties already predefined for air. If you should go ahead, you see other properties, like the basic properties, several properties in here. Analytic. If you should plot this, you see all these values of it. So now we'll go to move to electrostats. Let's bring it up here. We want to okay. We want to add a count to our electrostats. Electrostatics, we want to add a ground. So for our ground, we want to highlight, let me close the section. Now we can highlight our ground. We want 2 to be our ground. This 2 is our ground. This section is our ground. Go ahead and we want to, we're going to add terminal. The terminal will be at the top. Want it to be for the membrane too as well. And the terminal type, we want it to be a circuit. So done over here. Go to component and let's add another physics. Let's go to AC/DC and let's go to electrical circuits. Let's go ahead to add this electrical circuit to our work because of the terminal that we've added. So go to the ground node. Electrical, let's add an external coupling. That will be external I versus U. So the external device, we want to change here to terminal voltage. And we want to, the node for the, and we want this to be 0. Go ahead, look at the external, we want to add the resistor. The P node will be 1, N node will be 2. And the resistance, as we define in our parameters, will be the RP as we define in our parameters. When you define this in our parameters. Go to electrical circuits. We want to add a voltage source. So for the voltage source, make the P side 2, N side, make N side 0. Also change the voltage to V full as we defined in our parameters. Let's electrostat. Okay, let's come to the thermoviscous. Thermoviscous. We add the pressure to it. We are the 5 section. Then the pressure P0. We add the pressure and we go to thermal or multiphysics and we add this thermoviscous acoustic structure where we select the membrane. Also, structure is at the membrane. Okay, let's go to the membrane and let's show everything is at the membrane. Look at the axis, thickness, offset of the membrane. We want to define the thickness to Tn. Go to the membrane, linear elastic membrane, and you want to specify the Young modulus to be user defined to be m. Also want to specify the Poisson ratio to NUN. Also specify the density to be of HON. We've already defined all these in our parameters. So we want to add an initial stress strain to linear elastic membrane. We want to define the incline force to be Tn. 0. Also here should be seen as the initial force. Go to membrane. I want to add a fixed. Let's add a fixed constraint to 6. We've added a fixed constraint to 6. And let's go back to membrane and let's add phase load. I think we want to add, I think we have to add a phase load to this. We want to add a phase load to our membrane. So after adding a phase load, we select the membrane. Then define the force type. Okay, this is user defined, that's good. Now the R is US dot dn, like this. Good. So this is the load type for our force, the R and the Z. Go back to our membrane. We want to add another phase load. This is the second phase load that we are adding. Which will also be the membranes, and we have force per unit area. We want this to be pressure. Adding a pressure to, we want to define here as this to be length to bracket pin, which is defined as the external incident pressure. So over here, oh, I didn't define it. Yeah, you have the pin over here. External incident pressure. So phase load 2. Okay, so what do we do next is we go to, let me see, let me close all these. Go to definitions and we want to add the moving mesh. Add the moving mesh. Let's add a deforming domain, which would be for all domains. And we add a fixed boundary as well. Yeah, 2 and 7. So 257. We add I think we want to add, after this, we want to add, we want to add a symmetry ruler to 1. We want to add a prescribed mesh displacement to our membrane. We want to prescribe the mesh displacement as U. We want to the prescribed mesh displacement to be W. WM for our mesh displacement. Okay, so after doing all this, we go to the mesh where we add mapped adjust the edge mesh. Then we add distribution. For 3, and the number of elements wanted to be 30. We have another distribution for 6, and number of elements should be 4. We add another distribution. That will be for 4. You want it to be predefined. Number of elements should be 10. Element ratio should be 2. Symmetric distribution. Let's build selected. So we have this built. Okay. Go to mesh and add boundary layers. Make 4. Number of boundary layers should be 5. 1.2. We want a manual, and we want 2 microns. For our boundary layers. So let's build the selected. We have this. As you can see, let's make the transition rather. Let's take smooth rather and let's build. Okay. So we have our mesh system built. Now we'll add steady. We'll be adding a membrane. Okay, first we add an empty steady. First add an empty steady. Then we'll go to the steady steps and add the stationary. To add the stationary steady to this. And we'll add a frequency. Let's see, we add frequency domain perturbation. We have steady, stationary, we have frequency domain. Steady, we want to check this. As you've seen in here, then frequency perturbation, we have all checked. So we go to phase load 2 to see what we have here. Okay, we have this. Go to the frequency domain perturbation. And so we add the frequencies. We start from 2.5. Step will also be 2.5. We'll stop at 300. Okay. Let's look at the resolution. We use the solution from previous. We'll select now. Go to the steady and we want to add. Let's show the default solver. Yeah. Go to the solution store. File equations. We go to the direct and we want to change here to underscore. Okay. Also add a stationary solver too. You want to make here, select this to Cadisco. So move to steady one. And go ahead and compute our close the sites as well. You can close it and compute. It will take a very short time. Okay, so we have our results as shown in here. Go to steady. Metric potentials. Okay. See our stress. Okay. your activity stress. Add variables. You want to add a global evaluation. You want to take it from steady to solution 2. Now let's take it from solution 1. We add an expression electrostatics. Here's the voltage terminal to the second one, and we want the expression should be static solution. So we have evaluated scale values in there. The evaluation, frequency, terminal voltage, and terminal charge. Okay, so generally that brings us to the end, but we can make several plot groups as well. You can add a 1D plot group, you can add a 2D plot group. We add a 1D plot group. We want to plot a global expression, put an expression in here, 20 times the log of 10 es dot e equals 1. Okay. Okay. That brings us to the end of our work. By going to our model wizard, where we select our space dimension. Then we select our physics. We'll be using a lambda battery. So our battery interfaces, then lambda battery, which we will add. Then we move to our steady. Then we select the steady that we'll be dealing with. We'll be dealing with the time dependent. So we select time dependent and we are done. Which brings us to our interface over here. So we can quickly go ahead to load our parameters. So we click on parameters, then we load our parameters from file. So we'll call this Comsol. Which brings us here. So we'll be dealing with we'll be working with this parameter, this data, battery capacity loss parameters, which we'll go ahead to open. It gives us all our variables in here. We'll go on to our lambda battery. Also see what we have here. We want to change the operation mode to this. We want to change the applied voltage. We also want to change the battery cell capacity. We want to change the SOC as well. Then we are done in here. Go to the cell equilibrium potential. We want to clear, then reload. Our variable. From our file in here, we choose the capacity loss parameters. So we load this data. We change our reference temperature to T. We go to our voltage losses. So our temperature here should be T. We'll make our potential to change to 1C caps. So we go ahead to include concentration or potential. Tau should be so we can go ahead and add our capacity loss. In here should be user defined, then change our temperature to T. We change this to tau underscore loss. And we have to include our aging factors, which will depend on voltage. Change the offsets to sets. Change transfer coefficients to alpha. We want to include the aging history too as well. Want to make this caps G. We'll go back to our parameters to check. So all that we defined in there has been fully expressed and described over here with a description. The variable is the description. We move to our study and we want to name this as the calendar life. Yeah, the parametric C. We want to add parameter name, which we'll call the applied voltage, which will vary from 2. Add another parameter, which will be the SOC. 0.5. We move to the time dependent. We want to change the range for the times to make here 10. Two, 8. This way. be this way. Go to the calendar live. You want to uncheck the default plot and we want to compute this. So there was an error. Okay, so there was error that was detected. So we quickly identify the error. And we would like to change this to 3.97 our parameter value list. Then we can go ahead to compute. So that is the only section I changed. I'll change to we are changing it. Previously it was 3.94, now I'm making it 3.97. We want to compute. So there we have able to compute. The mistake was actually from this section. That was how come we're not able to compute our results. So we move to time dependent. We want to change our range as well. So we've already changed our range and want to, now that we've been able to compute it, now we want to add a 1D plot group. One D plot group to our work. Then go ahead to name this 1D plot group as relative cell capacity. Then our data set will change it to calendar life parametric solutions. We go on to add a global plot, which we want to change the expression to y-axis as LB dot Q cell this LB. This will go on to describe it as the relative cell capacity. We want to change the axis to maintain as time and rather change the unit to A. It should be time. Legends should be manual. Show should be 25% SOC. Want to make this to make this 50. We'll make this 100. Go on to plots, then we have our plots. We move to our relative cell capacity. We want to edit our title. None. Go on to change where our legends will be. We want it to be at the lower left. as we can over here. So we go ahead to our lamp battery. We want to see change the operation mode to as well to see how it will be. We want to make it a charge discharging cycle. We want to change the discharging cycle to LB. V dot I1C. It should be caps. Should be a negative. This minimum voltage should be minimum. We want to include the reset period. So want to change the resting time to rest. We want to change the charging current to C. So these are some of the changes that we are making over here. The dump battery section. We want to also change the maximum voltage to this definition. There should be curves. We want to also change the resting time. The resting time in here too as well. Want to change it using the same resting time that we're using over here. And we go on to include the capacity loss, make changes. Capacity loss. We want to include current at our capacity loss. We want our cycling capacity to be big H. Go on to add another steady to our work. We will choose a time dependent steady. Close this. We move to our steady 2 and we want to name this as cycle life. We use the same time for the steady one. We use that for steady 2. So we copy steady 2. Then we just change this to 1. Let's change this part to the 1. Go to the life cycle. Let me uncheck the default plots. Go ahead to compute. So actually solving. It will take some time. It will take a while, depending on the CPU of your machine. It takes some time though, so we cannot do anything aside. We wait till this is done computing. It will take some time, but it's very important we allow it to compute, to finish computing so that we can continue. This is taking quite a long time. taking quite a while to finish computing. All we can do is wait some time and let us finish computing. I'm sure for some computers it will take quite a long time, longer time than this. Some too will take shorter time depending on the RAM of the machine. tissue file. So I had to sort out something. Okay. Somebody help me also. I mean, I pay, so see. So, like, So we go to our global plot where we duplicate in here. In our data set, we select life cycle solution 6, where we change our legends. Change them to 1 cycle. Go to the capacity loss. Capacity loss, then relative cell capacity. That gives us our plot, so we're able to see our different charge cycle with the speed of charge as well. So that's the result of our work, the output that we got at the end of this work. So with this work, we begin with our new work, and we go to our model wizard. We select our space dimension. As 3D, we selected 3D, and which brings us here. We then select our physics. Then with lithium battery, so we select electrochemistry, which brings us a lot of options. We choose the battery interface here. We select lithium-ion battery. Since we've added it, now we move to our steady, and we'll be dealing with time dependence with initialization, which I'll add over here. So I'll save this as work, and we come to this interface here. So like I said, we select our 3D dimension and we select our battery interface, then steady time dependent with time initialization. So this is basically the interface definition, geometry, and materials physics, mesh steady results, and field. So quickly we go to our parameters and we select the parameters that we'll be using. We will load it from our file. So I'll load it from here. Go to local disk. Go to programs file. Go to Comsol. Physics. Applications. Batteries. Battery lithium. We're using pouch utilization parameters. That is what we'll be using. So we load it, and it allows us to add all the parameters that we're working with. So as you can see, all our parameters have been loaded over here. Cell height, tab height, everything, cell thickness, reference exchange, negative electrode, all these have been added over. So we are going to use these parameters to work for our work today. And it's very important that we always set our parameters right. Make sure all these things are in black ink. So we go to our geometry quickly, and we select our work plane. So when you select our work plane, it brings us to this interface, as you can see over here. So we select our work plane 1, and this is, after selecting this, we also come to our plane geometry, select here, and we insert or we add a rectangle since we are building our geometry. And we'll define what our height is based on our parameters. We know we'll be using these have already been named in our parameters. So W, each cell, then come to our height is also H cell. As you can see over here, then we build selected. So build selected, as you can see over here. So we do this using this parameters. So it's even over here, we can see our W cell, our H cell, and we made it rectangle W cell over 2 and that. So we go to geometry and we add another, we add this extrude to it. When we add our extrude, this is how it appears. We come to our distance M and we select this over here. So just as I'm continuing, we just do exactly what I'm doing over here. So follow up. So we are building our geometry and using these parameters. These are already defined. These variables are already defined in our parameters. So that's what we do at distances. And we make sure that all these are well placed, they are labeled correctly. If afterwards, then we select on the build to build selected. So this is how it looks like after selecting the build, after building this. I hope you've been able to build this geometry as I've done over here. We'll move to definitions. I would like to see the view using the camera here. Go to view scale and use manual over here. At the Y Z axis, select 100 and we update to see how it looks like. So as you can see, we've seen some changes that have been made over here after changing the Z scale over here. So this is a view of how our geometry looks like. Move to extrude. Selected. We have to add a block to our geometry. And the width, select. Our height as well. And also our done that for the depth, and we do that for our height as well, which will be this. We'll go ahead to build selected. As you can see. So after we input our width, size, depth, height, we also come here and we input the base, which is this. And after building, this is how our geometry actually looks like. So you just move the mouse around this geometry and you're able to see it in 3D, how it looks like. It looks very, very, very cool. Very cool, as you can see over here. So if you follow me as I've done, you'll be able to do it exactly how it appears. Secondly, afterwards, we just duplicate this. If we are block 2, then we just change the some of the positions over here. Over here, we change it to -h tab over here. Z to change to this. Just like this. Come here. Here it goes to 0. Here exactly how it was. Then we build. So you can see that actually included another part to it, as you can see here. So block 1, 2, okay. So I think you do it this way. You change, supposed to change here, and you bring it here. And you see what we have over here. We go back to geometry and build. Oh, that's how it should look like. And also definitions, and we add an explicit to our definitions. We'll name this label here as positive tab. And we're gonna select one domain over here. This is quite difficult to select the domains over here. We duplicate this positive tab. We change this to positive. That's all. Okay. Select 6 for that part. So that's we need. We duplicate this again. This becomes a positive electrode, which we select as 5. So whenever we select, we choose a domain, it actually highlights over here. You get to see how we actually duplicate again, which we name as the negative side. We select as 7. Another one, which that becomes our number 2. Now we label negative electrode, which is domain 3. Over here. We duplicate this. It becomes a separator. Move to we add another explicit to it. and we select our boundary. We label this as our negative tab and select our boundary 29. Duplicate this, which becomes our positive tab and it's number 2. Yeah. So this. Select both of these, a negative tab and a negative current vector. We label it as negative duplicate this. Unity form or positive as well. So choose for that our positive tab, positive current collector. It's highlighted over there. Then here, select negative current and negative positive, which we will add. Label as the metal domains. That's highlighted over here. Definitions, and we have a global variable proof. Name this as cell voltage expression. The name as sorry. So just like this. This is actually in yellow because we've not defined it, but as we move on, it will be defined. We'll define it later on. So we add our description, which will be our cell. We add a general projection as well. For our negative, we choose our negative electrode. It should be in small caps. We duplicate this as well. And this becomes our positive. So we choose our positive electrode. Then we go on to add a material from library. Go to add aluminum, add copper, now batteries, we have to choose our electrodes. We add LMO, we add graphite electrode. We go on to add electrolyte as well. And then we exit over here. Choose aluminum and allies. You see all the properties over here. So we have to select the domain for aluminum. Our domain becomes aluminum is at a positive current collector in tab, as you can see over here. That's a positive current collector. Like we said over here. Go back to materials. Same thing for copper. We have to also select the domain for copper, which is our negative current collector in tab. So that's for two electrodes as well. Graphite is at the negative electrode. It's at the positive electrode. Electrolyte is going to be at the separator. Make sure we've actually identified where our materials will be in the domain. We want to add a separator in our battery model. Select the domain for our separator, which will be at domain 4, which is our separator. Go on to select where our porous electrode will also be. That for the negative, select the negative electrode. So duplicate and we add before we duplicate, we need to add, choose the electrolyte material. So we define other properties as well. The electrode material to as well, we need to define it. before we define it, we need to, I want us to define the electrode volume fraction. Also define the electrolyte volume fraction. We will maintain this as a domain, then we'll move on to defining the particle interpolation. So the particle material will move to the particle mean center surface. RP, which is positive. Cross, come here and we move to the reference exchange current density. We're going to add an electrode. Which is a metal foil. Add electric ground. Don't add electric currents. Positive. This is wait. Is actually I. caps I. So need to keep note of that. So after defining it, you realize that this part that was actually previously yellow has now turned black, meaning it's been defined. We add initial cell charge distribution. Initial state of charge. Let's select the domain for the negative electrode selection. Do that for the positive as well. Becomes not applicable. Move to there and we add a porous electrode because we didn't add porous electrode. I would like us to bring it just beneath the negative one because this is going to be our positive, so it's appropriate to positive, and that is our electrolyte material. We choose as well, select as well. Make sure we select our electrolyte material. Now it becomes clear. It's a particle intercalation. Move to pros electrode reaction as well. And we change the reference exchange current density over here. Just to check if it's actually labeled every part and changed all everything that has to be changed. So we go on to mesh our geometry. Like to add math to help mesh our geometry. Select 20. That's how it does it. We move and to mesh, right click, and we choose the swept. Choose swept, not free triangle. So under the swept, we add a distribution to it. And highlight the negative electrode. And we actually choose a predefined number. And the number of elements, we choose 15. And the element ratio, we select 3. Afterwards, we go selected and we see how actually builds it for us. So actually duplicate, choose that for separator. is that 4. Build select. You actually get a little idea, better idea of how it looks like in your measurements. We choose our separator. After choosing our separator, big number is 4, which is 4. So this is our separator. We add distribution. Choose the positive electrode. So choose predefined 15 to 3. Add reverse direction. Electrode 4. Mesh in build 4. Into steady. Then we add a parametric sweep. Charge rate during simulation. We choose this parameter value list 1 to 4. The time dependent as well. We change this. To Sometimes. Once you are steady, then you compute. Okay, so there was an error in the computation. It was because of a mistake in naming one of the variable in domain 5, which is the positive. So I just located where that mistake was. It's at domain 5, which is the positive. So when you come over here, we can see Comsol has notified me over here that this is an unknown variable. I have to name it properly. It's because this has to be like this, just like this, before it will actually work. So this was actually the error. This was the cause of the error. So afterwards, if I should compute over here, it should run accordingly. So I'm sorry about that. That was a complete oversight. So this should start running. Okay, okay. Okay, okay. It's running correctly. No error now. So in case yours pops up or an error comes up, you should just check naming of your variables in the equations and some of the geometries that we've inserted. You just have to check maybe you did omit a letter or interchange one of the letters, so it would actually give you an error. But if you basically follow the procedure what I've given you, you should the model should actually work. It should run and it should produce results for you like this. So it will take some time depending on the CPU of your machine. Taking time, it takes a lot of time. So actually patiently waiting for it to finish running. Okay. So we have it now. Finally finished. And so this is how it should look like after Comsol solves this model. You should basically have this. This took about 5 minutes, 51 seconds. Depending on the machine, like I said, the CPU of your machine, it could take maybe either shorter time or maybe it might take longer time. Okay, so we'll continue looking at some of these plots. You add a 3D plot group. Name this potential in negative in tab, and this should be the steady one parametric solution 3 data set. time should be 0. Show legends, you show maximum and minimum values as well. And the manual color legend, I'll give us the color for this. So the potential and negative. I'd like us to add volume to it. We actually make here this to see how it looks like. Okay, yeah. But then we add deformation selection, not deformation, add further we add a selection. Select the negative current collector and tab. Plot. Position make it 4. And text color make a we have something like this. How about we find out for the positive? So we duplicate this and we find out for the positive. Find out for the positive and see how it actually be. Okay, so for the positive, that's how it should look. We add another 3D dots. do relative separator. We choose parametric solutions 0. The slides. Okay, so and over here when I get there, you have to choose an expression for it. Come back to you choose electrolyte current density. So so, so this gives us this, and we're able to put it. Choose you choose entry method, you choose coordinates, then you enter which coordinate you want to use to specify. So divided by separating, divided by 2, and you plot, when you plot, this is what we have. Relative, about we choose the time to about 6:30, and we plot after 6:30 seconds, and we plot to see what happens. At 630 seconds, this is what happens. Okay, results, we add a 3D plot group where we name as utilization. Probably the relative capacity put use a steady parametric solution 1, then we start at 2, 5, 0. Show maximum and minimum values. This, yeah. How about we add a surface? We add surface and surface plot. We add generate project positive at 0. Yes, yes, the average minus s yes, then add average of EPSS positive constant. And so so, so we have this here. Just to check expressions. It's really good. It's really good. So we go to surface and we add a selection. Okay. It's an error. Error over here. So I need to double check what I've done to see if everything is right. I think there's a mistake somewhere. Okay, thanks. It shouldn't be like this. I think there's still a problem over there. Where we choose our space, we're working with the 1D space. So we choose 1D. Then we choose our select our physics. So we want to use lithium-ion batteries. So we click on electrochemistry and we look for battery interfaces where we select lithium-ion batteries. Then we move to our study. We'll be dealing with time dependent with initialization. So we add to click our study. Done. It brings us to our interface, as you can see. So we look at our parameters and we want to load our parameters. Go. Programs files, Comsol files. Batteries. So we will be looking at choosing our parameters from here. So when you go to your programs files, applications, battery fuel cells, lithium ion battery, to bring it to this section where you have to load your parameters over here. And you can see we have several parameters that we can work with. There are several parameters over here that has been inbuilt in the Comsol setup, as you can see over here. So we will be looking at the battery, the parameters that we're working with is right over here. We're looking at battery multiple materials parameters, as you can see over here, and we load it. So it brings us here. And when you load it, you get all these parameters over here. So this is what we'll be working with right here for work today. We can go ahead to build our geometry. We add an interval, specify the interval, make it interval length, and we input what the length will be. We want to use LNEG, LSEP. We want to add L positive. Afterwards, we build the selected and it's been built over here. So afterwards, we can go ahead and add our material. We add from library. We choose our electrolytes first. Then afterwards, we add our electrode that we'll be dealing with. After adding your negative, you have to add your positive electrode too. So add our MO electrode too as well. And we close this material section. So as you can see, we have two positives and one negative. We'll look at the NCA, look at the basic equilibrium, and look at the interpolation. Let's see how it looks. As you can see, and we will also look for that of LMO, look at the basics, look at the interpolation, and we plot to see the difference. See, there's a huge difference between that. Go on to add our variables, which will load from our file. Load from our file right here, multiple materials variables. As shown here. So these are the variables that we will be working with in our work for today. So it's very easy to locate where your variables will be if you follow what I'm doing exactly. We go to lithium and want to add a porous electrode to our work, and we select the domain, which is the first domain. We go on to choose, we look at the, before that, let's open our material section, then to close the side. So at the porous electrode, we go down and we define the electrode material. So we look at the electrode material here, and we want it to be, we've chosen here, so we want it to be the negative electrode, because this domain already is indicated as a negative. And we look at the porous matrix. We want to define this, and you see Comsol has detected it as an unknown variable, as you can see over here. But later on, as we move on, it will be defined. Go to the particle intercalation. Very important, we select the material, which is a negative. We go to particle transport properties, where we look at the species concentration transport. We want to change this to the selection in here. Then we look at the particle mean center surface. We should use that of the negative. Look at particle discretization. We want to change the number of elements. We want to make it 20. In this section. You look at the distribution and we want to make it linear, the particle discretization. And we quickly move to the porous electrode reaction. We look at the material, we choose negative. We look at the reference exchange current density. Choose this. Specify this. Go to lithium. I want to add another porous electrode. We select the domain. We select the electrode material, which is the positive NCA. We change this electrode volume fraction plus NCA. Change this to X. Plus. We go to effective transport parameter. We make this user defined. Correction factor should be this. Positive. And that of diffusion 2 has to be user defined. And the same as this. So we did copy and paste over here. So we move to the particle intercalation. We choose our material. Select our material to be NCA. Move to our particle mean center surface, which we change to RP positive of CA. We change the species fixed or to Baker. We did change it to Baker, so we change this to this. And we go to porous electrode. We change the material to NCA. We change the exchange current density. Oh. All should be in small caps. Then NCA in big caps. is small cups. Right. Okay. We go on to add an additional porous electrode material. We select the domain. Then the volume fraction too has to be changed. Like this. Add the particle interpolation. And particle transport species as this. Concentration. We want to change this to solid phase concentration. Defined in here. We go to the porous electrode reaction one, then we want to define the material. We define the material. We have to select the material for this. So our material is positive. Also, we have to change this extreme current density to this. And we change the concentration to insertion concentration. Okay, so some input error, just the small caps has to be small caps I. So we go on to add a separator. Which will select the domain. Separator is this section. And we replace the volume fraction set. Then electrolyte conductivity is user defined. As you can see. Also, copy this, same for the diffusion, has to be user defined. So we place this in here. So we go on to add initial charge distribution, the initial cell charge distribution. We want to make this section, the initial charge, battery cell setting as state of charge. We input this values as SOC underscore cell. Yeah. And this section is also let's go there. No, this is but we move to the negative electrode selection, and obviously we have to select this section for it, that because that's a negative domain, and also do that for the positive, select the section. So after doing this, we go on to check where our value was in, it's still unknown. It's because of this should be underscore and it should be correctly named. So now that all our variables are, you go on to add an electric ground. Want to add an electric ground. We select a section. So it's this point that becomes our electric ground. Then we go on to add an electrode current. Add an electrode current to this as well, which we select where to be at the fourth. Go to defaults, and we want to click here and make our temperature T. We set it to T. We go on to mesh. We want, let's make it fine. Let's build. Okay. Let's go on to add an integration. Then we select boundary for this integration. We want it to be, so it's fourth. Let's name this integration as, we set the operator name to be a different name over here. How about we name it as end terminal. So we set that section. How about we move to the current? And we go to the time dependent and we change to 0 to 3, 6. We go ahead to show our default solver. And our time dependent solver. How about we change the times to store as this? And we go on to add a stop condition. We add our our expression. So this will be our stop expression. So our output at stop, we want to deselect and check this. And we want to uncheck the default plots. And we go ahead to compute. Okay. So we've been able to compute this. It has given us some results. We want to add a 1D plot group. Where we want to name this plot group as constant. discharge. We want to add a point graph to this. Choose to end. We make a selection. If actually can actually paste this and it will actually be the same. I can use this paste selection to paste it. Right, you can just click on it and good to go. We select the expression over here. Go to lithium-ion batteries. This is our expression that we should be using. Electric potential. When we plot it, gives us electric potential versus time graph of it. You can look at the plot settings. To check and change what should be at the y and x axis. On the y axis should be the voltage. The title we want it to be this. We want to make some edit the axis. So, as you can see, so you go on to add another plot group. We add a 1D plot group. We want to name this as surface concentration of positive. And we'll add a point graph. We will select this and go on to choose particle intercalation. Then is the after solid phase we have session. And insertion particle concentration surface. Legends we want to name this as NCN. We want to plot this. So we have our plots here. We want to duplicate this point graph. Want to change the expression over here. We want to select the insertion particle concentration. So we have our insertion particle concentration. This is what we'll actually select for our work. So we just double click on it. It gives us this. Or you can just type this expression over here and that will give you the same results. So we have our plots being done. We go on to the surface. Title, we want to name the title as want to name the y-axis as surface concentration. To do some editing of the y and x axis. Okay, so we plot this. We've seen some changes. We want to change the position of the legend over here to upper left. As you can see. So we go on to our steady solution. We want to duplicate our steady solution one. We want to name this as, but we change this here to take the component from this first section. Material tool has been changed. Go to our results. We want to add a 1D plot group. We want to make this a particle concentration, negative. We change the data sets to this. We do our time selection as interpolated. We need to add a range. To start from 0, step 200, stop at 2000. We want to add this to this. We want to add another range to as well. We want to start at 2032. Step will be 2030. Then 2200. Let's add it. No, we make this 2030 instead. We add another range. And this would be so we inserted or added our time range. We want to add a line graph to this. So we select one. Can also click here to select all, and we have to put our expression for this, which will be okay. So we want to plot this, and here we have our plot. Let's check the x-axis. Name this as normalized particle dimension. check this as well. We want this to be the particle concentration. And we want the title to be this. We add another steady. We go ahead to add a steady for this. And we choose a time dependent with initialization. Steady 2, we want to change here to 600. We want to add the parametric sweep to this. We'll add the parameter for which we want to check it. So we choose this and we try to vary within these parameters. Go on to steady. We want to show the default solver. We go to over 3. We want to see the time dependent solver where we want to make the output times steps taken by solver. How about after that we add a stop condition. We input the expression, which will just be the same as, this expression. So you can copy and paste, but I'll type it again. Stop. 1 dots and that's the expression. Stop expression. We want to uncheck this, add warning sign. Okay. We want to also uncheck our default plots and begin to compute to get our results. we begin seeing some results. So we have our results. Now we go on to add a 1D plot group. We name this as voltage profiles. Voltage profiles. We'll make it parametric. We add a point graph to this. We take the data set from our parametric solutions. Highlight, select this point. Now expression will change to the electric potential. Our legends, we want to show manual volume 5 mix of NCA and LMO. (5/7) mix. That's 55/45 mix. And we have 75/25 mix of NCA and LMO. We have 5/25/75. Then we go ahead to plot. As you can see, we have our plot of electric potential time showing different volume mix of our electrode materials. When we go here, we want to change the y-axis to change our y-axis here. I want to name this as just the voltage and we want to title should be manual because voltage profiles for different mix fractions and for NCA and NCA and for. So after that, we want to manually edit the x-axis and y-axis. Bring this to 0. Bring this to 3 and bring here to 0.2. We plot. Okay, so now It makes it more better. Then we want to change our legend position to the lower left. You can see over here. So we've been able to see how mixing different positive electrode materials will have on the voltage on the battery during a period of time, and we've been able to plot these voltage profiles for different mixed fractions of NCA and LMO. Also made a surface concentration plots for the NCA and LMO electrode materials. Also, we're able to do some parametric study on how these different mixed fractions will have on the voltage over a period of time in the battery. So I'm glad we're able to produce these plots in this work that we did today. Okay, so thank you for your attention, which will be 2D. Go ahead to electrochemistry, where we want to select corrosion secondary. So we go to corrosion deformed geometry, then we select secondary, corrosion secondary to our work. So we want to add this physics to our work. This will be using a secondary current distribution. Move to our study, where we choose a time dependent with initialization, which brings us to our interface. So quickly go to our geometry where we add a rectangle. We want to add a rectangle, and we want to draw our rectangle. 0, 1. Same here. We want to choose the position as minus 0.01. Then we go ahead to build our geometry. We go on to add another rectangle to our work, where we also make here 0.01. Our height should be this plus a little change. We want to add a little change to our work. So 1, -4. So we just want to make a little change to the height, and also to the position as well. We want to make a little change to the position as well, which we go on to build selected, as you can see. So we have built our geometry. Go ahead to booleans, and we want to make a union out of this. So we select both. We uncheck this. So we want to join these two to make it one. Those selected, and they are joined together, as you can see in here. So we can see that we've joined our two rectangles together to form single unit. We can load our parameters from our work. We load parameters from file. We'll be using galvanic corrosion. Using galvanic corrosion. I like to search for galvanic. So these are parameters. We found it. That's galvanic corrosion with deformation, as you can see. We load our parameter. So after forming our geometry, we go on to add an electrode surface for work. So we add an electrode surface where we select where this electrode surface will be. So we select 2 and 4 for our electrode surface. We check the species conservation. Check that. Let's open to check all these sections. Okay. Then we can now go to the electrode reaction. So temperature from the model inputs, the equilibrium potential, we put in this expression. That's also our kinetic expression. We want to use a cathodic Tafel equation where we change our I not exchange current density to this. We change our anodic current density to this. We move forward. And we go on to add a second electrode surface. So the second electrode surface will be here. And go to the dissolving species where we add a barrier. We want to name this as MG. Then this is rho MG. Go MG. So that's what we change in here. After we go to the electrode reaction, where we number of participating electrons, we make it 2. We set this to be 1. We set the equilibrium potential to be this. kinetic expression is made as the anodic tuffle, which will be IO underscore, and this is anodic, which will be N as shown. Add a limiting current density, which we'll define as ILIM anodic, as shown, as we've done in here. So that's for the electrode reaction. So we want to check what we did earlier. Want to cross check and see if actually named everything as supposed to be. Our electrolyte itself, we go to electrolyte conductivity, where we make this user defined, and this has to be sigma as shown. Go to our multiphysics deformed geometry, check. Deformed geometry. So things set in here. Geometry, deformation also sets. Move to the non-deforming boundary. For the initial, go to the second. We want to select only 5. So we want to select only 5 for this. So we want to select only 5 for the deforming electrode surface, and we want to, for the non-deforming boundary, will be the rest as shown here. So we go on to check isolation. Everything sets, then we can proceed to check our time that we want to set. We want to set our time from 0 to 12 times 3600, and we want to end at 3 times 24 3600 as shown. This could be very clear for us. So we can go ahead and compute our work. Which generates our results as shown in here. So we've been able to generate our results as shown in here. We want to add a 1D plot group. 1D plot group to our work. Which we want to add a line graph. In our 1D plot group. So we want to select the data set from our steady solution 1. We want it from the remeshed. We want to select, as we've selected our solution, steady solution 1. So view our solver. We check our meshed. Okay. So actually, we wanted to, in our time dependent, wanted to make the steady extension an automatic remeshing. So I've actually gone there to do automatic remeshing and want to compute it again so that we can get that result because we need a remeshed solution. So I'm recomputing it so that we can get our remeshed solution. Because it's very important for our work. I just went to time dependent, came here. Okay, now so we have our remeshed results. It's very important to allow us to plot our results. So now we have our remeshed solutions. Now we go to results, we add a 1D plot group and we add a line graph. Now we can add our steady remeshed solution. So that was exactly what's needed for our work. So our time selection, we want to select from the first our work. And we want to select here. We want to select from 2, 4, and 5 to 4, 5 as shown in here. We want to change our expression in here to cd.I log under ER1. That'll give us the local current density. If we should plot, this is what we have. We have in this plot. So I want us to close this space in here. Then our x-axis data wants us to change the parameter to an expression so that we can use an expression of x in here for our work. As you can see. So actually make it look this way. So we want to duplicate this work and we want to start from last. Let's plot and see. Okay. So from last, we've had our plots. We want to plot our work. So let's go ahead to open a file for this galvanic corrosion with deformation, which will open and add. We want to view as we have seen over here. So we go to want to add physics. We want to add physics to our work, new physics to our work. So we go and we add new physics to our work in here. So our physics, we come to chemical species transport. We go to transport of diluted species. We add to our work. Where we define the variables. We want this to be 2, we want our concentration to be CMG. We want this to be COH. That's done in here. We want to add a moving interface. That's under mathematics. We add level sets. To our work. Go to the parameters. And we want to load from file. We want to load our parameters from file, which will be under deposit corrosion parameters. We've actually added these parameters to this. Our definitions, we want to add a step to our work. Smoothing, we want our size of transition to be this. So we want to add variables which will actually load from file. We want under deposit corrosion variables. This is not defined, but later will be defined. Later be defined as we move on the course of our work. Definitions, we want to add non-couplings and general extrusion as shown in here. We want to select, we want to select a boundary for that. So select boundary. Our source frame, we want it to be this way. We want to use source map. We go to advanced and we want to set the tolerance to the closest points as much as possible. In our general extrusion, go to our transport of diluted species. We want to uncheck this convection. We want to make it migration. Move to transport properties. And we want to define the diffusion coefficient as dm on s dot bf2 plus dm e on s dot afl. And we want to also define okay, so this is 1. Okay, now it's defined. The diffusion coefficient as well, DOH S dot VF2 plus DOH E LS V F1. The full stop before this. We want to change the electric potential as well. We want to define it as Q. The charge number, we want it to be 2 and -1. Initial values 2 as well. We want to make here COH4. Sorry, this is 0. As shown here. We go on to want to add reactions. We select our domain and we define a reaction should be R as delta this also is R is called OH. It's not delta. Go to our transport diluted. Want to add concentration to our work. We select boundaries and we define our species to be H0 as defined in here. go to transport, and we want to add, move to surface reactions. We want to add electrode surface coupling. Choose 2 and 4 for our electrode surface coupling. The reactions coefficient, we want to change this to local current density. For this, it has to be local current density. Number of participating electrons, we want 4. And so the section 2, we want it to be 4. Go on to add surface reactions, and we want to add another electrode surface coupling. So this is the second surface coupling that we're adding. When we select 25, we go to the reactions. Same here, we choose the second region. The number we want to for this section, and we want to start from -1 here. Because go to the level sets. We want to look at the level sets model. Where we define the reinitialization parameter. It should be this max for as shown in here. We've defined our parameter for the reinitialization. This side, we also have to define the parameter for the controlling interface thickness, which should be LSHM. We set the velocity field to this value. Set this to this value. This expression. Move to the initial values, and we set it as the fluid 2. We want to add an inlet. The inlets we select 2, 4, and 5. And we go on to add, once we've added an inlet, we have to add an outlet. Very, very important. What's that audio? So we want to add an outlet. So after selecting our outlet, we need to select which area our outlet will be, because we've already chosen where our inlet will be. So we select our outlet, and the outlet will be the outer areas, will be from 3, 6, 7, and 1. That will be our outlet. Go to our secondary electrode. We want to define our electrolyte conductivity, add an expression to it. That will be LS dot BF2 F2 plus sigma F1 BF2 BF1 plus short linear. Go to our mesh. We want to add edit physics induced. For the first size, we want to make this calibrate for fluid dynamics, as we want to do for the first one. We want a finer one. For the second one, we want also extremely fine. We want fluid dynamics, extremely fine. Wow, work. So we move to our free triangle. We want to add, I think we have to add a side to this. Add a side to our free triangle. And there should be for a boundary. We select 2 to 5 for our boundary. Pretty fine should be extremely fine. Let's build and see how it looks like. So, seeing how it looks like for now. We move to 31. We want to uncheck certain areas like the deformed geometry. We want to uncheck this. We want to uncheck this as well. We want to uncheck these two. And we want to compute. Let's get rid of this. It should take some little time to compute. So wait patiently for it to compute. a while. Now, so wait for it to compute. To take some time. Take some time. We wait a while for this to compute. Take some time. We wait a while for it to compute. It's we wait for some time. It's actually taking a while. It's taking a lot of time. Really sorry about that. But we can't continue unless we're done computing. So I'll plead with you that we actually wait. I'm sure yours is not also done yet. So we're almost 50% through with the computing, still computing. Patiently wait. So wait, I think we're almost done. Almost done computing. Finally, we're done. That's great. We have our results now. Took about 9 minutes. So we click on electrolyte, look at the streamline, and we want to see the positioning. We want to do a separating distance of about, let's make it about 0.035. We want to also make the range. Okay, the range is 100. We want to plot, let's see. And here we have our results. We go on to the surface to our work. We put an expression as 1 here. Then we select our coloring. We want it to be uniform. We want our coloring to be uniform. We want it to be gray as well. Go to the surface and we want to add a filter to our work. We want to name this filter as LS That's 2 5 1 greater than or equal to 0.5. That will be our filter. We want to plot our filter. So when we plot our filter, this is what we have. You can see our filter in it as shown. We want to add a 2D plot group. We want our data sets from our remeshed solution. We want our data set from our, we want to select our time from about, let's say the last time in here. This is what we want to select, and we want to go ahead and add a surface to our 2D. We want to put this expression in here, and we'll go ahead and plot. This is what we have. We go ahead and add contour to our work. Contour to, we want to change the expression in here to s dot bf1. Unit should be 1. Labels should be, we have entry, or then we have labels, total levels. So let's make our entry mode levels, and want this to be 0.5 as shown. Let's change our color table to different color. Let's say uniform. Make it black in here. And plot. So that brings us to the end of this work, and I hope you're able to plot our work, able to follow till the end. Thank you. And please kindly subscribe if you haven't, and if you have any questions, please kindly drop them in the comment sections. And don't forget to like the video. Thanks. So we start by going to our model wizard, select new, and we select our space dimension, work with the 3D, which we select. Then we come here to select our physics. So we're actually going to use a secondary current distribution for our work. So we go ahead in here, when we choose under electrochemistry, we have primary and secondary current distribution. We have tertiary current distribution. So we go just under primary and secondary current distribution, we select the secondary current distribution. Then we go ahead to add this. Then we move to our steady, where we have to select our steady. And we'll be dealing with the time dependent steady. So we go ahead to choose time dependent with initialization. which we add. So this brings us to our interface, our Comsol interface, where we have added selected our physics and our study. So we go ahead to add our parameters. We want to reload from file, programs file, Comsol multiphysics, applications. Then I think we can search decorative plating parameters. So when we search for decorative, it will quickly search for our parameters. Then we load it, we open, we add to our file, as you can see in here. So we've been able to load our file quickly, as shown over here. So I think we can go start to build our geometry. We go to geometry, right click, then move to insert sequence, which we go ahead to add. And for our sequence, we'll be using the decorative plating geometry for our sequence. So this is our sequence that we'll be using for our work. So choosing decorative plating geometry sequence, we open, load. Okay, so now we have been able to load our sequence. Then we go ahead to build all. So that builds our geometry as shown in here. Want to show transparency as well. So as you can see in here, we go to materials. Check for materials also. We'll add our materials later, not now. So you go to secondary current distribution and you want to change the current distribution type. We maintain it as secondary for now. We'll be making some changes as well at the electrolytes. Also, we want to change the electrolyte conductivity to user defined, where we want to set this to K PPA. Yeah, as shown. So we want to go back to secondary current distribution. We want to add an electrode surface where we'll add to our work. So after adding your electrode surface, you go ahead to choose the domain. So we want to select domain 4. This where we selected to be our electrode surface in here. So as you can see, there are many sections. We have the film resistance. Now we move down to boundary condition. We have the perturbation amplitude. We have the external electric potential. We have different expressions that we can actually change them to for the boundary conditions. We have average current density, total current, and many others that we can actually change. So we are maintaining it to be the electric potential. Now for dissolving depositing species, we want to add. So we go ahead and select this area. This is where we're able to add our species. So click on to add, and it has added a species to it. So we have S1 being density as this, and molar mass as this. So we've added our dissolving depositing species to the electrode surface in here of our work. So like I said earlier on, we selected domain 4 for our electrode surface in here, and we went ahead to add the species, but we want to modify the variable for our species. We want to define it based on our parameters. So we go ahead to define it as n I. We want it to be the RO, RHO, and I. We want this to be molar mass of Ni as shown. So we go ahead to open the subdivision for electrode surface. Then we go on to check the number of participating electrons, stoichiometric coefficient for dissolving depositing species as well. We've seen that what we change when we change the variable over there, it has been defined over here. We want to change the number of participating electrons to 2. We want to change this side to 1 as well. And this is the equation that Comsol will solve it with. Goes down. Then the equilibrium potential changes to this Q on the Ni. Then move on to the electrode kinetics, where we want to choose, before that, we want to choose the local current density. So we go to electrode kinetics, then we select our expression type to Butler-Palmer equation, and change this current density to this underscore nickel I Ni, non-nickel Ni. So we've changed the current density this side. And move ahead to add, to duplicate this electrode surface. We have a second. Move to the electrode reaction, where we compare, but before that, it has to be changed. The domain has to be changed. It has to be changed to this. That's for the second surface, and also the phase has to also change to average as shown over here, and this expression too has to change to this as shown in here. Then move back to here and also the coefficient has to change to 1, has to be 1. So we go ahead to the electric surface and we want to add a reaction. We've added a reaction. We've added a reaction to this. Okay. So move ahead to the reaction. Then we want to move to the number of participating electrons. We'll move to the potential. We also move to the kinetics. We change to cathodic. Current density has to change to this. Change this section to this. Then we go ahead to the mesh. As shown. So we want to change the element size to a final. We want to build all. Able to build. Go to our time dependence, our current distribution initialization. And we want to change this current to secondary. Then our time dependent, we want to change the output times. Let's change just this section, 60 and 600. Then we go ahead to, we can study now, compute. So we've been able to compute, then we move to our results. So we move to the selection. We want to select just a particular area, which will be the boundary. We want to select this. I want to plot to see. So that gives us the thickness change. I want to rename this plot to the projected thickness cathode. We want to duplicate this. We want to rename as the current efficiency cathode. We renamed it. We want to look at the surface and also change the expression in here to CD RLOC underscore ER1 CD.ITOT. As shown. We've changed the expression in here. Then finally plot final work as shown. So that gives us our plots for our work. Okay, so we would like to determine how to check the capacity fade in a 1D battery model. So we're going to use a 1D battery model in Comsolmultiphysics to predict the capacity in the battery over a period of time and its aging over a period of time. So at the end, we should be able to plot some results showing the capacity cycle with respect to time, how it changes with respect to time, and also the state of charge as well. So we should make a plot of this as well during this study, showing the discharge curve comparison over a period of time, different cycles, and also the cell voltage during discharge for different cycle numbers. And also we should be able to make a plot of the state of charge at the separator and the electrode boundary, different cycles, the first and the last cycle for the different electrodes. And finally, show the plots of how the capacity ages or varies over a period of time. So let's get started. So at the beginning, to our new, go to our model wizard, then from our file, we look at our application library. So when we open our application library, it brings us to this place where we choose lithium-ion batteries and we select capacity fade. We select the capacity fade seed. We open. So when you open, it will take you to the interface and you see or everything defined variables. As you can see, variables have been defined over here. So it's actually inbuilt. All these things are inbuilt in the console setup, depending on the model that we are using. Let's go to lithium-ion battery, those electrodes, everything. You can see it has already been, the domain has already been selected. Open our particle electrode has actually been defined. Most of the variables have been defined. To the porous electrodes. So this is basically how it is. And if we should check the materials, we see that it's actually added materials to it. The electrolyte negative and the positive electrode have been added to it. Go to the initial cell charge distribution. You can see everything has been input over here. So we go ahead to add the charge discharge cycling to it. That will be the first work, and we'll select our domain as form. That is all we select for this section. Discharge current, discharging current we set as -I. Minimum voltage we set as E. Maximum voltage will be max. Our charging current will be set as this. Then we check this side, which is include constant voltage charging. And we set this side, which is the upper cutoff, as charge. We would like to start, we go to the start mode, and we want to start with the charge first in this section. Move to porous electrode 1, where check to you want to add SEI as rho SEI. We want to make this here this way. That's our dissolving depositing species. Set it as SEI and define the density and the molar mass as well. We go ahead to check this add volume change to, we uncheck this part. And also the film resistance, we want to change it to thickness and conductivity so that we can define the reference film thickness, which we define this way. And we also want to change the film thickness. We want to change it to total film thickness this way. Film conductivity, we want to change it to this. Move to the porous electrode reaction 1. We check everything. Then we go and we add a porous electrode reaction to the second one for porous electrode. So over here to go to the electrode kinetics. Then we make here user defined. So we can input our I. Let's go on SEI. Cycle. And let's go on number greater than 0. This way. Move to our variables. We check to see if everything is defined. As previously, those which were in yellow are now black. Everything is now black, as you can see. Go back to porous electrode reaction 2. And we check our coefficient over here, which will make it T underscore factor minus 1. That is geometric coefficient of v I theta. We go to our parameters and we check our t factor, that's time acceleration factor, actually 250, yeah. So move back to our first electrode 2 so that we can set our SEI to be t underscore factor. Our temperature should be user defined. We go on to definitions to add an integration. Where we select the negative electrode. We move to our steady. And before that, I want to show default solver. We move to our current distribution initialization. We want to check if everything is line, but first we will actually modify this part and go ahead to disable our pros electrode reaction too. So you could either click here or just disable right here. So now it's disabled. Our pros electrode reaction too. So you go to current distribution, then you go on to disable pro selector 2. Let's open this solver on our time dependent solver. Let's add a stop condition. So we want to add a stop condition to this. That cycles. And you also want to add change this part to steps before and after solver. This section, we want to uncheck this part. Move to our steady. Want to uncheck generate default plot. So before you study, you need to go to, you need to check all the areas to see whether there's no mistake, especially for the pros electrode reaction 1 and 2. So we check that it should be thing that I've done over here. Material should be graphite, equilibrium material, kinetics as well. This way carefully set it. So this was what we made some changes over here. At the equilibrium potential should be user defined, kinetics user defined, so we go ahead and compute. We have our convergence plot. So we have this. So So we move on to let's close this. I want to add a 1D plot group. I want to add a 1D plot group to plot some results, which we'll name as load cycle. Name this as load cycle with the title type of the nine. Plot to y-axis. Our load cycle, we want to add global. We want to input this expression, I cell. So now variables I cell is already stated. Move to global. We want to duplicate this. We want to filter as well. We want to put a logical expression over here as first cycle filter. It's been stated in here. We move to global 2. And we want to delete this global 2. Just maintain this global 1 and duplicate it as well. I want to check this. I want to change this expression here to E. When we plot, this is how it should look like after plotting. We want to add 1D plot group. Change the expression to discharge. Is comparison. Our title to none. Y-axis, rename it as cell potential. Want to add a global. I will name this as the first cycle. Input this expression E cell. Direction. Want to change, check, and make the parameter an expression. So we input our expression as T as this. This will be our expression for our parameter. And we go ahead to filter and we check this as fair cycle filter charge filter. So this has to be, let's go. It's just a star over here. Fair cycle filter. It's a filter here. Yeah, and you're able to plot it. Move to the variables. See, first cycle plotted. Go ahead to duplicate this. How about we check the last cycle? And make this description cycle go to 200, 2000. And we go ahead to filter make this the last. So we plot, we see. That's the cycle for. So we make here description cycle for 1. Make the comparison a bit better. We plot. This is the first cycle, and this is the cycle for 2000 to 2000. Go ahead to add a 1D plot group. Change this to SEI. Layer potential drop at 1C. Change title. Y-axis. And we change the title to this. And go ahead to label the y-axis as potential drop over let's make this potential drop over CI layer. Go ahead to add a point graph. Select what we want to check. We put our expression in here. Change your parameter to an expression. Change the expression over here to cycle number. Change the description to cycle number. Change the things to at negative electrode current collector. We move ahead. After adding move to add a filter to it. So we label this as PCH dot filter. We'll duplicate this. In this selection, change it to here. We delete this. And here is that of the separator. To show our legends as well. We duplicate this and change this to electrolyte. Y-axis label changes to electrolyte interaction. And go to our points. We'll change this to yes. We change that of when you have two down. One plot, we have this. Plot, we have this graph. I want to add another one, the plot group. Which we'll call capacity fade versus time. So capacity versus time. I'll try to be none. Y-axis show the time and days. And show relative Capacity. Go ahead to add global. This becomes Q minus 1. Q score differential Q of 0. Change the parameter to expression where I name this as T E score pattern. Let's choose E. Description. I want us to choose time as base ratio legends to now. And we want to show this as based on level 18. Go ahead to add a filter to this. Yes. Charge. Filter. Want to duplicate this and to C1 dot T underscore D which starts change your legends to nominal 1 to charge capacity. So we will duplicate this. Change this to versus cycle number. Change this to cycle number. Expression change to cycle number. Send this to the scene. We plot add another one D plot group. Sorry, local state of charge at separator electrode interface. This manual. Y-axis is SOC. We add a 4-point global. We add a point graph instead. So select put the expression SOC OC underscore surface SOC LOC. This is right. Make sure everything is right. Parameter expression. We choose to cdc.t underscore switch. That's we want to show our legends. So need to show this photo. It's probably let me retype this again. Make your so legends show negative electrode to first cycle. Let's add a filter. It will be the first cycle underscore filter. I want to duplicate this point. And graph. I want to select deselect this and select side 2, 3. This will be positive. We want to duplicate this again. And change the filter to, I want to duplicate and change the filter to last. Sorry. Last. See. I want to duplicate this point graph 2 and select it's already selected, so select again here. Okay, so we have 4. 1, 2, 3, 4. Already selected. Already. We move to, want to check how variables will actually look. So in our battery, we go to how about look at cross electrode reaction. So this shows the local current density.